everyone. My name is Sarah Cooley, and I'm an assistant professor of geography at the University of Oregon. And today I'm going to be speaking with you about my research tracking global surface water variability and the influence of human management using ICESat-2. So as most of you probably know, the combination of climate change, population growth, and economic development is really increasing pressure on global water resources. Because of this, it is more important than ever for us to be able to understand how surface water moves and is stored around the planet, and to better kind of constrain our freshwater resource availability. However, obtaining the observations of water levels at a global scale that are required for global analysis of freshwater variability has been limited by the coarse resolution of satellite radar altimeters, which are only able to observe the world's very largest lakes and reservoirs. So this may have changed, though, a bit in October 2018 with the launch of ICESat-2. So ICESat-2 is a NASA satellite that carries a laser altimeter known as ATLAS, and it provides really highly accurate, high spatial resolution observations of surface height. These observations have a 17-meter point footprint, so again, really high spatial resolution. They're split into 6 beams, which each beam there are 3 pairs of 2, and there's a 3-kilometer spacing between the different tracks with a repeat cycle of 90 days. Now, as you might be able to tell from both the name of the satellite or from this image shown here, ICESat-2 was originally primarily designed for use over ice sheets to track how ice sheet height and hence ice sheet mass loss has changed over time. However, ICESat-2 collects data all over the world, not just in the polar regions. And so we wanted to see how ICESat-2 might be used to look at changes in water level. So to do this, we intersected ICESat-2 data with reservoirs located in the continental US in order to see how accurate and whether or not ICESat-2 could be used to look at changes in water level. So this is an example for a reservoir in Kansas. You can see the different black lines here. Those show the ATL03 product in the 3 different ICESat-2 tracks. And then the red dots are where we've intersected the ATL08 product with a water mask of that reservoir. And on the right, you can see that, because water levels tend to be, or generally are very, very flat, that ATL08 product does a really good job of capturing the water level quite accurately. And in fact, when we do this analysis across hundreds of reservoirs located in the US, which also are gauged by the USGS, what we find is a really strong agreement between changes in water level observed by ICESat-2 and changes observed from gauges, with an RMSE of 14 centimeters, which is really quite excellent, given that observing changes in height from space is kind of notoriously really challenging. So this tells us that ICESat-2 has a lot of potential and could be quite accurate for looking at changes in water level. So now that we know that ICESat-2 data has value for observing changes in water level, our real research question we were interested in was how seasonally variable is global surface water storage, and particularly how much are humans contributing to this variability. So to do this, we first needed to create a global data set of surface water levels from ICESat-2. And naturally then, the first step was to use a water mask to input to this analysis. And we started with the Peckel et al. 2016 Global Surface Water Occurrence product, but we edited this mask pretty significantly for a couple of reasons. One, we wanted to ensure that we were only looking at lakes and reservoirs and ponds, not looking at any rivers. And also we needed to ensure that our water mask was quite conservative, so we could be really confident that any ICESat-2 retrievals that we retain are measuring water level and are not contaminated in any way by land. So we do some modifications to this GSWO data set. And then the next step is to intersect the data set with the ICESat-2 ATL08 product, or the surface height product. And here's an example of what this looks like for a reservoir in California. So the different colors here represent different days. And so each day is split into 2 different tracks. That's because of that paired beams that ICESat-2 has. And you'll notice that our retained water level measurements, which is represented by each dot, are clearly located within the water boundary because we wanted to be quite confident that we were only observing water. Now, the next step was then to filter our ICESat-2 observations. And this is really important both to ensure there's no contamination from land, but also to remove outliers that are generally present in any kind of data set or any satellite-derived product. And in particular, there are 3 key criteria we were looking for in terms of filtering out observations. So first, we wanted to ensure that all observations retained have at least 3 ICESat-2 points in the same track on the same day. So you need at least 3 points in that track over the water body for us to retain the measurement. We also ensured that all measurements had a same day, same track standard deviation of less than 0.25 meters. This is a really important threshold, and you can read more about the sensitivity analysis we performed and our choice of this threshold in the paper. We also wanted to ensure that all water body observations retained were less than 3 standard deviations away from all other observations of that water body over our study period. So the combination of these 3 filtering criteria made us confident we were able to remove most outliers. The next step was to aggregate to monthly time steps, so to create a time series, and we used a monthly time scale for a couple of reasons. One, because of the multiple tracks in the same day, we needed some sort of aggregation period, and this allowed us to filter out observations for large lakes, and also provided a standard time period over which to perform the analysis. And then finally, the final step was to calculate the variable that we were, of course, interested in out of all of this, which is the seasonal variability in water level. And we calculate this quite simply as just the maximum minus the minimum water level observed over our study period. Now, as you'll notice, because ICESat-2 has a 90-day repeat cycle, these time series look pretty sparse. We don't get ICESat-2 observations every day or not even every month for most water bodies. And so as a result, our observations of water level are underestimations of the true variability simply because we're not observing it all the time. We did a bunch of analyses on this. You can read more about it or talk to me more about it. I'm happy to discuss, but just know that we are quite confident that even though the numbers reported are likely underestimations of the true variability, the overall global patterns and conclusions are valid and would not be too much affected by increasing the number of observations. So in total, when we run this analysis over our entire study period, we're able to calculate lake level variability for 227,386 water bodies over a study period of October 2018 to July 2020. Here, each dot represents a water body. You'll notice that most are located in the Northern Hemisphere. That's just because there's a lot of water bodies there. That's where most lakes are. But we do have a global sampling and we observe water bodies all over the world. And importantly, this data set includes lakes as small as 0.016 square kilometers, which is really quite tiny and orders of magnitude smaller than what you can observe with other spaceborne altimeters, and really emphasizes, I think, the uniqueness of this data set and just how exciting this technology is that allows us to look not only at the largest water bodies, but also really small, even ponds as well. So when we analyze this data across the entire world and put it together by water basin, by hydrologic basin, what we find is that the median variability in water level is 0.23 meters. But of course, these values vary quite significantly by region. We see pretty low variability, as you might expect, in the northern high latitudes. These areas have not a lot of seasonality in precipitation and also are typically not as hydrologically dynamic as other regions of the world. Whereas in contrast, in tropical regions or in areas with monsoon environments with really high seasonality and precipitation, like the Amazon, the Congo, the Indian subcontinent, even the Western US, we see water level variability averaging a meter or more across our study period. And we find that for the 40 largest river basins, the median variability ranges from 0.2 meters in the Nelson, and you can see that most of these hydrologic basins with low variability tend to be located in the Arctic or at high latitudes, all the way up to 1.5 meters or more for basins like the Amazon, the Orinoco, the Niger, even the Colorado in the Western US. So that kind of gives us an understanding, an interesting insight into global seasonal variability in water level across hundreds of thousands of water bodies. But what we're really interested in is not just how variable water level is, but really how much humans are controlling this variability. And to answer this question, we intersect our data set with 2 different reservoir data sets, one being grand and the other being good. And these allow us to identify which of our water bodies have levels that are in some way controlled by human management, and therefore determine the proportion of variability in water storage associated with humans. And what we find is that across our entire study region, across the entire world, reservoirs are responsible for 57% of the total global variability in surface water storage. Put another way, 57% of the variability in surface water storage occurs in reservoirs or in water bodies whose water levels are in some way modulated by humans. And this is despite the fact that reservoirs only account for 3.9% of all of the water bodies that we analyze. Now, I'll note we're able to move from water level to storage by multiplying level change by area. And Similarly, as with the patterns in water level, we see quite a bit of regional variability. So in northern regions, we see where there's not a lot of people and not a lot of reservoirs, a low percentage of the variability is associated with humans. We also see low percentage of human impact on water storage in some rainforest basins that have a lot of water bodies and really high seasonal variability, such as the Amazon, the Congo, or Indonesia. But over most of the world, and particularly most of the world where a lot of people live, so most of the heavily populated, densely populated world, such as the continental US, Indian subcontinent, East Asia, Western Africa, Southern Africa, parts of Europe, parts of Australia, we see that humans account for 80%, 90% or more of the total variability in water storage in these regions. So really a very large effect over much of the world in most places where people live. We can similarly plot these patterns for the 40 largest river basins. So here you can see that really low percentages of variability is found in places like the Congo or in Arctic river basins like the Mackenzie. In contrast, there are basins, heavily populated basins like the Ganges, the Mekong, the Rio Grande, the Colorado, San Francisco, where 95%, even 99% or more of the variability is occurring in reservoirs, which really emphasizes just the degree to which humans are modifying the hydrology of these basins. So we can also look at how these patterns vary by country, just to reveal some interesting, patterns about, global hydrology and management. So it probably doesn't surprise you to see that India, which has huge numbers of reservoirs and huge numbers of people dependent on reservoirs, as well as highly, highly seasonal precipitation, has 99% of the variability occurring in reservoirs. And we see similarly high levels of variability occurring in reservoirs in places with arid climates that are highly dependent on reservoirs for water usage and irrigation, like Iraq, Australia, and California. But there are places in the world like China, Canada, and Peru, where even though these places all have large reservoirs whose levels are heavily regulated, there are many more natural water bodies, and therefore, the role of human management in those basins or in those, regions seems to be smaller than in, somewhere like India or Iraq. So a lot of interesting patterns and more detail to be had from this data set. But overall, I think these results really emphasize the dominant effect that humans have on global surface water storage across the planet. This figure is from a really interesting paper that came out a couple of years ago that looked at how we portray the water cycle in textbooks and in classrooms. And what they found is that humans are often absent from depictions of the water cycle. And our results emphasize that humans actually play a large role, at least in this water storage component. We see that humans actually exert a dominant control on seasonal variability in water storage. And it's not just water storage, right? Other aspects of the hydrologic cycle are also now really being strongly affected by humans. And so I think that emphasizes maybe a need to change how we talk about and teach the water cycle to acknowledge the large role and perhaps the increasing role that humans are having. I also want to note that this study is really intended to serve as a baseline as well. So, ICESat-2 is a relatively new sensor, and we're getting some exciting new satellites launching in the next couple of years. And I think what this means is that as we get more and more data, ICESat-2 collects more data, other satellites like SWAT collect more data, we'll be able to even more accurately quantify these variabilities in both natural water bodies and in human managed water bodies to understand how things like climate change and increasing demand for water are affecting global water resources. So I think there's a lot more work to be done, and I hope to see even more accurate analyses of this data set in the future. Finally, I just want to conclude by highlighting one particular way, I think, in which we're working on improving upon this analysis. And that's by combining ICESat-2 observations with sensors like Landsat, Sentinel-2, and PlanetScope, which provide us with time series of lake area. So the blue curve here is a lake area time series. This is for a reservoir in California. This is Sentinel-2 data. And the red dots show the corresponding height observations from ICESat-2. And when we combine the area observations with the height observations, we're able to create a rating curve or a relationship between water level and reservoir area. And this allows us to create time series of storage change from space. And what we find is that these time series have pretty good agreement with gauge storage. It's not perfect, as shown for this example, but it's close enough that it gives us confidence that we'll be able to observe these patterns at a global scale. And that will really allow us to extend the time series, extend the time period, and also get a lot more temporal detail in terms of understanding how surface water storage is changing both in reservoirs and natural bodies around the world. So I just want to conclude by saying that I hope that I've demonstrated to you the power of ICESat-2 for observing surface water from space, and that there's a lot more work to be done and potential for ICESat-2 in the future. And if you'd like to collaborate or speak with me more about it, please reach out. I'm always happy to chat. Thanks very much for your time.